Good evening, everyone, and welcome to our Yosomi webinar series. It's 7 o'clock in Rotterdam, sharp, so I want to start this webinar. I'm Pinar Yilmaz from Rotterdam, and I'm a Yosomi Young Club member and member of the webinar committee. And currently I'm working remotely as a research fellow for the JPK Stroke Center in Boston. And today we have a great guest, a colleague of mine from the Erasmus Medical Center, who will enlighten us about explainable AI and distributed learning. I will co-moderate this webinar with Anna Andreychenko. She's an MRI physicist and she got her PhD at the Utrecht Medical Center with her research focus on 7 Tesla human MRI. And currently she's working on developing a methodology for safe and reliable introduction of AI in radiology at the Moscow Healthcare Department. This webinar will be recorded and can be found on our YouTube channel together with previous webinars. We would also like to thank Bracco for sponsoring this webinar. And I will continue to introduce our speaker of today, Gennady Roshchupkin. Gennady is leading the computational population biology research group, which develops and applies methods for the integrative analysis of large-scale biological, epidemiological, and clinical data. The group uses the latest approaches in genomics, medical imaging, computer science, statistics, and machine learning to sort through increasingly rich and massive amount of data. So we are very happy that Gennady has kindly agreed to share with us his valuable experience on explainable AI and distributed learning. Furthermore, we have a Q&A box, dear attendees, so if you have any questions, please write them over there and we will discuss them together with my co-moderator at the end of the webinar. Please, Gennady, go ahead. The floor is yours.
Thank you, Pinar. So it was really nice. Thank you for introduction and also thank you for inviting me today. So a really great pleasure. Today I'm going to talk about explainable AI and distributed learning. So that quite exciting areas of research, and I think that's they somehow related but also unrelated to each other. And this is I think that ongoing really fast developing in these two areas of artificial intelligence. So I will try to cover some topics today and give some general introduction and some references and some insights in this field based on my knowledge and experience. But of course, in this such a short webinar, it's difficult to cover everything, but I hope you will find it helpful. Yeah, so, and myself, I'm working on the, well, medical data. So it's also omics, MRI data, X-rays, and health record databases. So I will try to cover some topics mostly related to, let's say, radiology research in my presentation, but also sometimes it's easy to make examples with some either like real world examples or some other domains of the medical field. So, okay, so artificial intelligence. So that's what we're going to talk today. And actually, once I got your attention about artificial intelligence, so I actually want to make a point, a remark that, well, artificial intelligence sounds really fancy and big. And I like this slide where it shows the history of the development actually. Such field, it started in the middle of the 20th century as a huge excitement and a lot of hope that in a few years the humanity will have real artificial intelligence. So let's say basically the machines which can think and behave like a human, but it didn't happen, and it didn't happen, haven't happened till now. But what most of the time people talking when they say about the artificial intelligence, that's about machine learning or deep learning. Deep learning started to become more and more popular, let's say, in the last 10 years. And just to start with some introduction, why, let's say, it's so popular, and especially deep learning becomes more and more popular. So if you compare the machine learning, where, well, this is just, again, as I said, some real world example or two example. And so if you want to use machine learning for prediction of the based on the image for classification, let's say car, not car. So in machine learning, normally you have to pre-select some features or measurement or parameters and then input it to the different machine learning algorithm of your choice. Let's say in this example, like a decision tree, and then this decision tree can make a classification. Is it like car or not car? So what is the difference between deep learning and machine learning? Then actually in deep learning, you don't care about this feature selection. So you just basically can pull all your data measurement and features together. An idea that this neural network can do the feature selection together with classification simultaneously. So, and it actually does work really well. So, and many fields and many applications. And in last years, you can see a lot of examples, especially actually in the radiology and other medical domain, where you have image analysis, because it became a really state of the art in image analysis of such algorithms, because they're really fast. They don't require a lot of, again, as I said, feature selection, or, well, they do require some data cleaning, but it's another story. So, and you see that there are a lot of applications, like a publication, also even the software which already approved by FDA for using this data. So that's why the deep learning is really a huge thing in the medical, especially image analysis field. But just to remind how it looks like, so when we're talking about the deep learning or neural networks, that you have input data with some input layer and input parameters. Then you have a hidden layers with neurons, can be fully connected. It can be have a convolutional layers, and actually there are now like tens of different type of the network architectures which you can use. But the basic idea is that you have input data, you have some magic going on inside the neural network with hidden layers, and then you have output which you can use for regression or classification analysis. Well, in some cases with image analysis, you can use it also for segmentation. And just to demonstrate you, let's say again, so real world, just two example, when you do a classification of the handwritten digits. So you input your 2D image, which has like some pixels, like two-dimensional data. You just use a fully connected network, and you can see that while going through this network, different neurons are activated, and then the network makes the final prediction. Of course, you need to do some training first for such a network, and then use test data set which was not used during the training for such type of the, let's say, visualization. But the problem which you can already foresee that, well, with this architecture, it's kind of, you can see some layers activation, some features, but if the network becomes deeper and more complex, then even if the classification or prediction is very accurate, we have the problem which we can't really say why the network works in a certain way. So basically what we call a black box problem. So, and especially in medical field, the question is, why should I trust you? So why I should trust this model? So even if it works correctly, there might be a lot of biases, confounders, etc., and also just difficult to understand. And here comes the field, which started to emerge like several years ago, let's say, more intensively. That's you can call it explainable AI. So an idea behind this that, well, on the left you see that classical problem when you have your input data, there's something going on inside, and you have your output data. And what we want actually to get, we want to have a model which works as good as the left one, but which we can understand why it makes certain prediction. And like we can call it visible neural network. And what I want to talk today about the ways, first in the first part of the presentation, the ways how we can do this. And one of the way is just what we can call reverse engineering of the neural network. So, and the most popular and straightforward way to do this using the so-called heat map activation maps, or like GradCam method. So in this example, you see that, let's say in the middle, you have the input. So input image, and on the side, you have the heat map for different classes. So in this case, this network trained to make a distinguish or like prediction for cat and dogs. And you see that when we are predicting cat, so the heat map focus on the cat. Well, that's nice. And when we want to predict a dog class and an image on the right, you see that network heat map, let's say, focus on the head of the dog. So that sounds really great. So that this type of the algorithm works basically after you train network. It doesn't really matter what kind of architecture of the network you have. You can always try and apply such method. And I have a good example from radiology application. So we did deep learning prediction for the brain age based on the gray matter MRI images. So we just use a convolutional deep learning network, try to predict age of the subject based on just MRI, and then also using the additional covariates as a gender. So and then we link this brain, let's say age, and your biological age, the difference between this prediction to, let's say, to link this difference to risk for Alzheimer. But in this application, we also use the GradCam method. So basically, after you train network, you can backpropagate your prediction per every image, and then you can average the heat maps. And basically, what we got after this, we got the image of the gray matter template with highlighted brain regions. And that also looks, well, as we expected, let's say, for the brain age and Alzheimer risk or dementia risk of development. So you see that the highlight regions focus on the temporal lobe and specifically on hippocampus. That's really nice. The same as I showed you with the example of the cat and dogs. But there is one thing which you should take into account when you're using such type of the reverse engineering, that explainability is not the same as interpretability. So the first thing that the neural networks, they are greedy algorithms. So basically, when you have a heat map, so you can't make conclusions that that's the most, let's say, you can make conclusion that network looks at a specific part of the brain or specific part of the image, but you can't make conclusion about that the rest of the image is not actually important for your specific task. So let's say we come back to the example with the brain, right? So that we made conclusions that hippocampus is important, hippocampus area based on the heat maps is important for risk of dementia, but we can't actually claim that the rest of the brain is not important, because neural network, they just greedy, as I said, and they just, if this is enough information in this area to make a prediction accurate enough, so the network will not search for other part of the image for the prediction. So let's say therefore for medical application, you should always think about this and take this into account. And second is that, for instance, GradCam can be used for explanation, but it does not guarantee that this explanation will make sense for you or for medical application. So let's say that if you're trying to use some images for prediction of the let's say patient survival risk, and then you input some random images to your network. The network can learn the parameters, let's say, like related to the like MRI scan or X-ray scan or the actual surrounding of the patient. So say, you're making images of the patient like when they're laying or sitting or standing, and of course the network, for instance, can learn that if the patient is laying in the bed, that's more severe, but it has nothing to do with other like factors. So you should always take this also into account. And interpretability is something different. So then you can link it to your research or your medical question. Let's say if you go to the classical application like logistic regression or linear regression, actually interpretable, because you can the parameters or covariates you use, they make let's say some sense if you find significant association in betas or odd ratio, so you can always interpret this. So that's also keep in mind. Therefore, actually, you can also use a different way, knowing that the deep learning algorithms are greedy. So what you can do, you can use a different approach. So that's an example of research we are doing. So we have X-ray scan of the let's say kid's skull. This is a healthy skull, and this skull where you have well, you can call it also fingerprinting. You see that there's a certain pattern there in the skull. So this copper beaten appearance. So, and that can may be related to certain health outcomes. So, but the idea that we want, for instance, to segment and let's say train network to pay attention to the whole pattern, not only part of the skull. Because, for instance, if you just segment, if you pay attention to the part of this fingerprinting, so that might be enough, but we have more in the skull, let's say, which we want to segment. So, and we end up with approach actually knowing that the whole skull shape is not important. So we know that this network will focus on the pattern which in small patches. So then we decided, okay, so let's just split the image to the small patches and randomly shuffle them. And then you can use this as an input to your neural network, but also actually it can be additionally used as the data argumentation. And basically what we did, so that network just does prediction to every patch. Does it have a fingerprinting or not? So we can train network this way, and then per every patch we know that network, let's say, makes a classification, but also breadcrumb analysis. So, and then later what we can do, that we can just combine together back, let's say reconstruct the original image back, and then we can see the heat map which covers all the pattern in the skull, not only, let's say, if we would use just original input, so that, for instance, will be only frontal part will be on the heat map of the breadcrumb, because that's enough to make a classification between healthy and fingerprinting pattern. But that's just some examples of the reverse engineering or knowing how the deep learning works to do this, to make this interpretable. But there are actually type of the architecture of the neural networks which can be used for directly for interpretation. And one of the such architecture is autoencoders. So that's again this image as example. So the principle how autoencoder works is just that you have input data. So in this case, it's also handwritten digits and also noisy. So, and then you're trying to reduce dimensionality to the latent space in the middle part of this autoencoder. And then you try to reconstruct just using the information from the latent space. So the idea that you assume that there is some correlation for your input data, and therefore you can reduce the dimensionality. And after you have the reconstruction and you see that you try to reconstruct as good as original image, but also, for instance, you can remove the noise. So how you can use it in the medical image or some image domain. So actually that type of the networks you might know that they are really widely used, like in Instagram and Snapchat, to analyze your facial images. So what we did, we used actually the same type of the network, but we have in Erasmus MC, we have a 3D images of the facial data from elderly population, also for kids. So we use the same approach, but for 3D data, and we did this reconstruction. And why it's interesting, because these latent features, latent space, can be used to explore their relation to certain pattern on the input image. And that's why I chose the face as example, not, let's say, MRI or some other domain, because it's really easy to interpret it. So basically what we can do, we can link these latent features to specific covariates or specific factors, and then we can easily change this to sample from this latent space, and then we can see how the input image would change. So we can fix one of these features. Let's say we can fix BMI and change gender. We can fix height and change BMI, etc. So in this way, such type of the network, they are fully interpretable, because, well, because you can see that latent space features, how they link to the different input image parameters. So, and you see that here examples like we have, I think in the original method, we have 200 latent features, but then here you see that just example of how many 18 first features. So in each of them has a different pattern on the face and different location of the face. So, and the same approach, of course, can be used for other medical image domain, but I just chose face as a really clear representation how it works. But another way, actually, is to build your, so this is a type of the network which can be used for the interpretation, but another way is actually from the beginning to start to build your network architecture based on the biological or medical knowledge. And here I will, well, I think that still, let's say, it's a good example from not from medical images, but from genetics data and omics. So basically, when you build your network based on the biological knowledge or annotation. So you have genetic variants, you know how they connected to genes, you know how genes connected to different pathways, and then you can like integrate other information, how this is related, and then you do your prediction or classification. So, and why such type of the data is interesting then, that each actually neuron in your network, it does represent some biological unit. So which makes sense. And then later, after you train your network, you can basically cut each of your layer and see based on the activation of your neural network neurons, which one is the most important. And if you integrate more information, you can also make just a summary which one is the most important. So in this example, what we use for, let's say, genetic data, omics data, but you can think the same architecture, let's say, for other domains. And I saw examples also with brain segmentation, let's say, where each neuron represents some brain region, and then a brain region, and then you do your prediction or classification, and you see that some neuron is activated for, let's say, Alzheimer prediction, and then you see that this neuron actually represent voxels from hippocampus. Yeah, so, but of course, there's just some examples to give you some impression. But as I mentioned, the field is really developing really fast last years, and there are a lot of methods if you Google about like interpretability of machine learning or deep learning. And I just want to cover in this presentation, given the time, just a few of them, the most popular, at least based on the GitHub repositories and the papers published. And I want to start with sort of LIME. So it's like local, interpretable, model-agnostic explanations. So basically what it means, I will describe the figure just in 1 minute. So it means that this algorithm can be used to explain your prediction. For it doesn't matter what kind of model you use, it's actually machine learning or deep learning. And what it does, if you look at the picture, so let's say you have a really complex pattern. So the 2D dimension, the dimensionality, you have blue and pink or pink, let's say, area, which represent your two classes. Let's say that the blue is healthy and red is, or pink, sorry, is disease patients, for instance. And of course, to estimate why network makes this complex pattern is quite difficult. So in this method, what the other did, they say, okay, we don't want to estimate the whole, to model all this complex area. We want just, if we focus on specific example, let's say in this case, on this figure, like this red cross, that's one input image. So we want to know why specifically this one red cross, let's say, image was classified as diseased and not as healthy. So, and then what they do, they just sample examples which are based on some metric close to this input image. Let's say you see that in other crosses or in other circles. So, and they just locally, so these dashed lines, actually that's local approximation, like linear approximation, why this classification was made between crosses and circles. So they don't look at the whole, let's say, search space, they look at the specific examples. So, and how it works, basically, so if you have input image and you want to classify, let's say, electric guitar or the dog, so then you can interpret the network that it works, which part of the image was important for like guitar classification or for the Labrador. Another popular library for the interpretation of the deep learning is DeepLift. So it works differently compared to the GradCam and some others. So it uses information about the activation of different neurons in the deep learning. So in this figure, you see on the left the input images, and this in the on the top you see different classes what it could be. It can be from 0 till 9, any digit. And then in the box, you see that how network looked at this image to make the classification. If you look at 2, so let's say for 0, 1, there were almost nothing interesting for the network. But for the class 2, so network really looked at all pixels to make the classification that this image belonged to 2. So, and the same was with 1. So for 0, there's nothing interesting. And for class number 1, there was like a lot of pixels are important. And let's say what you can see is interesting to look at the 0. So basically it's 0 network look that there is a huge empty space in the middle. So, and it makes sense because only for 0 you have such empty space in the middle. So it's immediately classified as 0. And for 4, the same, you see that 4 class, this is important pixels. But if you look at the most important pixels are on the top of the 4. So because there's also empty, there is no lines. And that's important for the network, if you think about this, to distinguish between 4 and 9. Because if there would be a line on the top, so the network would classify as a 9. So this is an example, let's say, for the application gain. So the deep learning for the handwritten digits. And another library actually, which integrates the two previously mentioned together, but also much more. So this is Sharp. And I really suggest to take a look at the paper and also GitHub repository. It's really popular and used a lot. And basically, they combine together these approaches where you use it for different machine learning methods, not only deep learning, but also like random forest and others. So to open this black box and to show which parameter actually are the most important for the prediction. And again, so they also integrated this deep lift method, so to show which pixels are the most important for the prediction. In this case, they just show the two most probable classes, and you see that network look at the face, well, on the head of the animal, and then let's say the shape of the bird. And but of course, it's just, again, as I mentioned, some just real world examples, but this library is widely used for also clinical application. It was like a recent paper in Nature Communication about that, using the electronic health records actually to explain the deep learning prediction. And you can see that's really nice visualization about, like, okay, you have a lot of parameters about your patients, and then you can reverse your network and to see which one is the most important. Well, in this example on the bottom, you see that this is like the size of the circle represent the importance for the prediction. Also, a recent paper about actually breast cancer survival prediction, also using the SHARP method. So here you see that network was used for gradient boosting and for the Cox proportional hazard. So A is a Cox proportional hazard analysis, and B is a gradient boosting machine learning method. And also you can see which parameters were the most important for the survival prediction. So every dot on each figure represents one person. So you see that, let's say, age is a really important factor for both type of the analysis, but there are other parameters when you can make a summary and see which one is the most important. So that's just a summary of the method. And again, so let's say I suggest to take a look at the GitHub or repositories and papers of the method I just mentioned. But here we come actually to the second part of the presentation. That's everything is really nice, that we can, well, eventually it looks like we can do some interpretation and explanation of artificial intelligence, but we all know that this algorithm is really greedy for data, and therefore we need a lot of data actually to properly train and remove all the biases and actually, well, train well our network. And here comes the approach, which also nowadays really popular and developing really fast, what we can call federated learning. And we just had a discussion just before the call about the difference between federated learning and distributed learning. So in literature, you can actually see that they quite mixed together. So, but there is a difference. So federated learning, I would say, just a more global definition. But just to give you impression, what is actually federated learning is, I think most of you familiar with just classical meta-analysis, which you can perform based on the literature or based in the consortium. Let's say when you share some summary statistic or you share some betas, standard error, p-values, and you can do meta-analysis. So here you see that, let's say, green boxes represent like the different size of the analysis where they did their analysis, and then they share with central site these betas or p-values, and then you can do meta-analysis. So, well, actually that's idea of the federated learning, when you don't share the raw data, because I think all of you are aware that in medical field it's quite difficult to get all data in one place due to many factors, but such approach can solve the problem, because you don't share, you don't have access, nobody has access to the all data, but you can do the meta-analysis for instance. This is a classical way. What is the difference in machine learning and deep learning? That all this basically sharing the data and communication should go through over the neural network, over the internet, over network, and they should be done simultaneously. let's say in the federated learning workflow. So what you have several steps where you share the architecture of your network with all sites, all cohorts, all hospitals involved, and then they train locally and they share it with central site aggregates all data and basically update the weights of your network or machine learning methods, and then share it again, and then you have this loop till the network converge to the good performance. So this is, you can see this on the left side. So this is an example of federated learning. And actually on the right side, you see where example of the workflow where you don't have a central site. So everyone, so it's like a peer-to-peer computation. So everyone shares with everyone and then aggregates and then share again. So this is actually a distributed learning example. So you don't have a central site, everything is distributed. So, but at the end, you also have the final model, the final performance as accurate as you would have all data in one place, but you just don't share again raw data in both left and right example. And if you go a little bit deeper in the details, federated learning might have a different topology. So as I mentioned, that the most popular in this case is like A and B. So it's like centralized or decentralized. But in some certain examples, you can think about some hierarchical or hybrid hierarchical model, which is really rare, I would say. And also there are different ways how you can compute your data again. So you can just sequentially share the updates, or you can still have aggregation node and then share it, or you can use like a peer-to-peer connection. And I want to mention just how you can do this, because there are various ways to actually to do this and train this, and there are several popular frameworks or libraries. So one of them is like open source Monai. That's actually really widely used for medical image. And there are a lot of networks already architecture implemented. Another is also Python library Sift, which also used a lot. And another one is popular and actually developed and maintained also by NVIDIA. So it's a Clara framework, which is freely used and supported by NVIDIA. And we actually collaborate with NVIDIA using this Clara network for our genetic application, and also actually what I showed previously, brain age prediction. So that also can be done distributed. That's also work done together with, we now collaborate with NVIDIA. And just to give you impression, so NVIDIA just recently, you can check their website. They did this distributed learning using Clara for the COVID patients. So that's quite an interesting user case. And just to conclude my presentation, given the time, that what you should always take into account, as I mentioned, that explainability is not the same as interpretability. So you should be always careful and know what you're doing and how you interpret your results. And if regarding the methods, what I just mentioned, several of them, several libraries today. So most of the time, you need to try several methods actually and compare results for the explainable, let's say, deep learning and machine learning. And you should know that the field is still developing, and probably will be more method coming in coming years. So you should just keep eye on it and try them out. Regarding federated or distributed learning, I think that it's kind of promising, and I think that's a future model for medical field, especially given the issues with data harmonization and data sharing for medical analysis. And what you should also think when you are using federated learning, there are, which was not covered in this presentation, some questions and some you should be sometimes careful regarding the privacy of the data, because of course, while for the network you don't have access to raw data, but there are different, let's say, ways to abuse this federated learning if you don't know or you don't trust the parties which are joining your federated learning, so that you can still reconstruct certain information about the patients, let's say. And there are also ways and approaches which are now developing about some encryption and privacy, like 100% privacy preserving. So that you should also take into account when using the federated learning. So, and with this, I want to conclude and say thank you, and I'm ready to answer the questions.
Thank you, Gennady, for this great overview and enlightening us about these matters. There is one question in the Q&A box from Arturo Moncada Torres, thanking for the talk, and his research interest lies in both of these, in the distributed AI and the federated learning. And he asks if if you have any experience where both are combined in a single project.
Oh, okay. So actually, no, I don't have example which you combine in the one project, but I can't think about, but might be some issues, but I don't think that it's would be difficult to combine them. In some way they are independent. If you can share, for instance, the trained network after you train it on the distributed or federated scale. So I don't see too many issues why you can't use let's say explainable AI on top of it. Only the with So no, I think that's the short answer would be like this.
Okay, thank you. There's another question from Juan Antonio Hernandez, asking, what do you mean with interpretability versus explainability? Because you had this one nice statement in your...
Yes, so as I mentioned that, so let's say explainability, it means that you can explain why your, let's say, deep learning model makes certain prediction or gives you certain results. So let's say you can say that why it does it, but this by definition does mean that it will make sense. Let's say interpretable in a way that it, especially for medical application. So that's, I think that's the difference. So let's say, as I said, let's say classical linear regression or logistic regression, you can also always interpret the results that I know, like increasing one standard deviation cause the increasing of the outcome to a certain also extent. So, but with deep learning, classical, if you use like a GradCam, that you can highlight certain areas, but they might not relate to your question. So you can give a really good prediction, but it might be related to, let's say like this. So that there's example where was a paper about using the skin images, photo images for skin cancer prediction. And eventually it happened that the network does predict really well, because on the images with the patient, we actually with the skin cancer, there was like a marker, black dots from the dermatologist always actually on the training set. So a network just paid attention to this part of the image, which has nothing to do. So you can explain why the network does this prediction, but it's not really interpretable for medical application.
So continuing on what you said before with the methods for explainable AI, which, because there are, you explained us about the beneficial parts, etc. So do you think it is applicable to all, or should we, like, if it's applicable, that we should do it?
You mean the application of the explainable part?
Mm-hmm.
Yeah, I mean that's That also depends on your question. So let's say if you interested just to achieve really good prediction, so then and you don't care about that why actually does predict really well. So then you just show that okay, we're using this data, we can reach the maximum prediction. That's it. So, but if you need actually to understand and like explain, maybe again, so for the patient or for yourself or for some other follow-up analysis, then of course you should use it.
So for if for example for prognosis follow-up of your patient and that prediction value has meaning or is going to be used in that sense, because the other prediction where it might not be that much of interest, for example, is just, well, what in I think within our center also has been done is predicting, for example, MRI markers. I mean, that prediction is high, but in the end, if
I mean, if you have a, let's say, the beauty of the, let's say, deep learning, that you have it can capture a complex pattern in the data. So, and if the human actually can't really understand this pattern, so then that's it. So you can interpret it or explain it, but that's just too complex, so it doesn't make sense for you, but it gives a good prediction. So even if you would apply this explainable method, let's say if you were talking about like brain MRI, so say there's some complex pattern with brain aging, like a global all cortex, subcortical regions, etc. involved. So you can't say that it happens only in like temporal lobe or some part of the brain. So it just has a complex pattern, which you can see eventually on this heat map, but it doesn't make sense for you.
Okay. And another question, what would be the downsides of the distributed learning versus conventional ones?
Well, as I mentioned, okay, first thing actually that's still takes longer because the training depends on the complexity of the network architecture and the amount of data and also, well, internet connection. So it can take longer. So sometimes, it can take much longer. So that's the issue. And I also think that there is will be a separate kind of field of research how to optimize your network for federated learning, because in-house you can make as deep as fancy depending on your GPU card, but on the federated scale you just want to make it simple and faster. So as simple as possible, but let's say not to reduce the performance, but just to reduce the complexity. And second, still, as I mentioned, might be issue with privacy. Let's say if you have if you don't really trust your partner, let's say, involved in this, so they can abuse this if they can, for instance, run the analysis, etc. So some parameters, if you brute force, you can imagine that you can reconstruct certain information about the patient.
Okay, thank you. There are more questions in the Q&A box. The Arturo Moncada Torres, who also asked the first question, he says, we are very well aware of the benefits of federated learning. However, as any new paradigm, sometimes we have a hard time bringing people on board, especially at hospitals. People are reluctant to switch to a new technology, particularly because of the work involved in getting a federated learning setup and running. And asks for your experience. What are good practices, tips, tricks to bring federated learning to real life scenarios?
That's a good question. Based on my experience with not only federated learning, I think it's good to have a pilot project where you can show people, look, that works fine and there is nothing scary, but it works actually better and you can get better results. And well, for this, you should have at least, I don't know, 1-2 partner in your this network who also enthusiastic and want to do this. Then once you have a good results, normally others just want to join because otherwise they will miss a publication. So normally
jump on the train.
Yes. So that's based on my experience. By the way, I think you missed one question. I want to know. Yeah, I think that's from Antonio. I want to know if you can do a heat map, explainable map inside of a tumor. Right?
That's the next question, I think.
Oh, okay.
That's from Antonio Lopez. Go ahead, you already read it.
Yeah, good small enough to realize which is the worst part of the tumor to guide a biopsy, for instance. Yeah, well, I think that we actually in Erasmus in bigger group there is a PG project about such, I think, that related to this. So where it's not, I'm not working myself with this, but there are there is some research going on about such type of analysis where it's not so simple, but I think that it's possible. Yeah. So it also depends, of course, on your training data and do you have enough patience to actually distinguish these parts. Yeah, but that's possible.
Okay, and then another question is, within radiology context, to what extent is it is needed the interpretability or explainability when have in a network making diagnosis with, for instance, 90-70% of success? Asked by Juan Antonio Hernandez. And then last part I can't read.
Well, I think, well, you should ask, I think, the radiologist.
In training?
Do they need this or not? So again, I think it depends on the task. So let's say if you just care about the accuracy and you don't care why. Let's say if, well, not maybe related to, let's say if you have deep learning for brain segmentation, even like gray matter, white matter, CSF. So if it does it really accurate, you don't want to, you basically, well, it's interesting from technical part, why it does it, but as radiologist, you don't care why that, how it works. So if you have such examples, I think that's, you don't need this. But if you do, for instance, again, so there's a previous example with tumors surviving, or like for the biopsy, or again for like Alzheimer or the dementia prediction, or also dementia, let's say, onset prediction. So that's, you might be interested in the part of the brain which are the most important.
Okay. We also had some questions for you. So what methods within explainable AI are the most efficient in your opinion?
In my opinion, well, I think that, as I mentioned, there are several ways. So, well, if you talk about the methods just for explanation, let's say, or interpretability, I think that, as I said, so it's better to try several methods just to see, does it make sense in your settings? And I think that Sharp method, which I mentioned, that one is actually like a library which integrates different most popular one. But I think that what we are working actually mostly ourselves on the type of the network architecture which can be interpretable. Let's say, like as I mentioned, this autoencoders or explainable, let's say, deep learning for like omics analysis, where every neuron makes some biological unit. Mm-hmm. So then you can see that if this neuron is activated and this neuron related to like certain gene or part of the brain, that's, I think, that most interesting application. But for if you want to use something out of the box, it's just better to try several libraries. And well, just also to be honest, they all not perfect because they use some approximations.
Yeah. Okay, thank you. And what about the minimal data sizes? What minimal data sizes should be available to to apply the distributed or federated learning efficiently?
For distributed, well, but for distributed, I think that's the same as for classical deep learning. I think as much data as possible. But it really depends on the domain and examples. I mean, like I know that for is a simple tissue segmentation, you might need just, I mean, brain tissue segmentation, you might need just tens of examples of like white matter lesion segmentation. But if we're talking about like brain age prediction, that you actually need really thousands, and because you also want to cover the distribution from like the whole lifespan, so it really depends on the domain.
Okay, clear. And what do you think that explainable AI will be able not only to explain to humans, but also teach them a new knowledge discovered from the data only?
Oh, well, yes, actually, that's interesting part. Yes, so because that's what, for instance, I showed with the face example, because we don't know, well, we kind of, as a human also, of course, we have feeling that if you see the face, you can say, okay, this is like male or female, or like, I don't know, like something about weight or height. But with this type of the network, because we can autoencoder and using this latent space, you can actually make a visualization and changes, and you can see, okay, this is a transition between, let's say, even you can make a transition between two genders, let's say, from the more feminine face to more masculine face, etc. So the same with other applications. So that can teach us about such patterns. And also based on my experience with omics data, because with genetic mutations, it also especially for like complex trait and diseases, that's kind of a pattern in your DNA. So it's not like one mutation leads to the Alzheimer's disease. It's just a combination of them. So that can teach us actually, about biology and etiology.
Yes. And do you think that explainable AI relates to radiomics?
Sorry, say it again.
If explainable AI relates to radiomics.
Radiomics.
Mm-hmm.
By radiomics, you mean, just to make it clear, so it's like, because I heard the different definitions.
Yeah, it was a question by our co-moderator, but unfortunately her mic isn't working.
Because I think that, well, I think that radiomics, in my understanding, that's about like also related to tumor analysis, let's say segmentation or prediction, etc. So, and I think that's what was already asked about, like biopsy and tumor growth prediction, etc. But yeah, that's definitely can be used.
Okay, thank you for your answers, and thank you again for this great talk, and everyone who attended and had these amazing questions. We also want to thank Bracco for sponsoring the webinar, and the webinar will be online on our YouTube channel later this evening or afternoon, depending on where you are at the world, I guess. So thank you again, Genna, and thank you, everyone. Have a great evening.
Yes, thank you so much for having me. So it was a really great pleasure. So have a nice evening.